Hello everyone, I'm Jiaoyang Li from University of Southern California. This is a joint talk with Andrew, Scott, and Joy from Amazon Robotics and Satish and Sven from University of Southern California. Our paper title is Lifelong Multi-Agent Pathfinding in Large-Scale Warehouses. Nowadays, in autonomous warehouses, hundreds of mobile robots are navigating autonomously to move inventory pods or flat packages from one location to another. The left video shows an Amazon fulfillment center. When you order an item on the Amazon website, a robot here will first move to an inventory pod that contains the item you ordered, lift the pod, move it to a working station, and then a human worker will pick up the item and put it into a package. Once all packages are ready, they are transformed to a sorting center, and the packages will be sorted according to the destinations in the sorting center. The red video shows a sorting center, and the yellow structures here are the chutes. Each chute corresponds to a different destination. The robots will first move to a working station where the human worker can put one package on each robot. Then the robot will move the package to its corresponding chute and drop it into the chute. In both applications, we need to solve a navigation problem in real time. The traditional method for solving the navigation problem is to use a single-agent pathfinding solver, where each robot plans its own path, and then the collisions are resolved on the fly using some simple traffic rules. For example, if two robots are going to collide with each other, we can simply slow down one of the robots, or we can plan an alternative path for one of the robots. This method works pretty well for easy instances. However, when the map contains too many robots, or when the map contains too many chutes or inventory pods, this method could cause heavy traffic congestion, just like the left video shows. Therefore, in this paper, we study the multi-agent pathfinding solutions. We propose a multi-agent pathfinding solver called RHCR, and in the same condition as the video show, our algorithm can schedule the agents very well, namely almost no traffic congestions occur in the simulation. So here is the structure of this talk. I will first introduce more details about multi-agent pathfinding and its lifelong variant. I will then talk about three existing methods for solving this problem. Then I will introduce our method, rolling horizon collision resolution, and last I will show some experimental results. Multi-agent pathfinding, or for short, MAPATH, is a problem of planning collision-free paths for multiple agents. The input is a graph and a team of agents, each with a start location and a goal location. The time is discretized into time steps. At each time step, an agent can either move to a neighboring location or wait at its current location. And our task is to find a set of collision-free paths, one for each agent, and minimize the sum of their travel times. MAPATH is hard to solve optimally. But people have still invented dozens of algorithms to solve this problem in the past decade. There are optimal algorithms, suboptimal algorithms, or incomplete algorithms. However, MAPATH is just a one-shot variant of the actual problem in the warehouse applications. Because typically, after a robot reaches goal location, it does not stop and wait there forever. Instead, it is assigned a new goal location and is required to keep moving. Therefore, we study the lifelong variant of the MAPATH problem, where agents are constantly assigned new goal locations. In this paper, we assume that there is a task assigner that is outside our path planning system, and the agents can request goal locations from the task assigner during the operation of the system. Now let's look at some existing work. So the first method to solve this problem is to formulate lifelong MAPATH as an answer-side programming problem. And then we can use any off-the-shelf on such a programming solver to solve it either optimally or suboptimally. However, there are two limitations of this method. The first one is that it needs to know all goal locations in advance. And the second one is that it has limited scalability. So in the paper, they show that their solver can only solve for up to 20 agents, and each with only about 4 goal locations. The second method overcomes this drawback by decompose the map path, the lifelong map path, into a sequence of map path instances. It solves a map path instance for all agents at every time step, where the start locations in the map path instances are the current locations of all agents, and the goal locations are the next goal locations for all agents. So this method can be applied in an online setting, which means that it does not need to know all goal locations in advance, and it also scales better than the previous method. But it also has some drawbacks. The first one is that it needs to replan paths at every time step, or at least at those time steps when some agents have reached their goal locations. So this could limit its applicability in some domains because planning could take time. The second drawback is that this method might do a lot of redundant or repeated work. This is because when it plans a path for an agent, it discards its previous path. Although people have invented some techniques to using some incremental method to save some search effort, but still, when the problem is very hard, it's hard to avoid the redundant work under this framework. So then people propose a third method where it plans paths only for a subset of agents at every time step. It assumes that when we plan a path for an agent, the agent will commit to that path, which means it will never change that path. And therefore, we only need to plan paths for agents with new goal locations. So this method scales much better than the previous two methods. But the drawback is that, first, it still needs to plan paths at every time step, or at least at those time steps when some agents has reached their goal locations. And second, because at every time step it only plans paths for a very small subset of agents, so it cannot coordinate all agents very well. So sometimes it could generate poor quality solutions. And also this method only works for a special class of maps called well-formed maps. Let's look at our algorithm, Rolling Horizon Collision Resolution, or for short, RHCR. We also decompose lifelong map path into a sequence of map path instances. But here we use a rolling horizon framework where we solve a windowed map path instance for all agents every each time steps. The windowed map path instance is different from the map path instance in the following two ways. The first one is that collisions need to be resolved only for the first W time steps. Since we replan the path at every each time steps, so we need to guarantee that the agents will not collide in the next each time steps. Therefore, W needs to be at least as large as H. The second difference is that an agent might be assigned a sequence of goal locations instead of only a single goal location. And this is because if the agent reaches goal locations using less than each time steps, the agent will wait there and doing nothing. So therefore, we will assign a sequence of goal locations to the agent to ensure that the agent will always be busy in the next each time steps. Many existing map path solvers can be easily adapted to solve windowed map path. And in the paper, we have shown how to adapt 4 popular map path solvers to windowed map path solver, namely CBS, ECBS, C*, and PBS. So for the first difference, for CBS and ECBS, because these two algorithms are based on a framework of planning passes first and then resolving collisions afterwards. So we only need to change the collision detection function. Originally, CBS and ECBS detects collisions for the entire time horizon, and now we only detect collisions only for the first W time steps. For C star, it's based on a framework where it plans the paths for the agents one after the other, and the passes planned later need to avoid collisions with the passes planned earlier. So now for the windowed MapPath solver, when we plan paths for an agent, we only consider the passes of planned agents for the first W time steps, so that we need to change the collision avoidance function. Last, for PBS, because PBS is basically a combination of CBS and C star, we therefore need to change both the collision detection function and the collision avoidance function. For the second difference, there exists an algorithm called multi-label A star that can find a shortest path for an agent to visit a sequence of goal locations. We therefore simply replace the A star algorithms used by the four algorithms with multi-label A star. And with these modifications, we can solve windowed MapPath instances. There are four advantages of our algorithm. The first one is that it works for all kinds of maps. The second is that it does not have to replan paths at every time step. The user can decide the value of the h. The third is that compared to the solver that resolves collisions for all time steps, our windowed MapPath solver can significantly reduce the runtime. The last one is that although we limited the planning horizon, we could still produce high-quality solutions. And this is because resolving all collisions within the entire time horizon is often unnecessary, since the paths of the agents can change as new goal locations arrive. Imagine that we are in a very busy warehouse, so at every time step there are some agents reach their goal locations and are assigned new goal locations. So even if we resolve collisions for all time steps, later when other agents have new passes, the passes of the current planned agents will probably be changed anyway. Now let's look at some experiments. We first demonstrate our algorithms in a simulated real fulfillment center. So the map we used is a well-formed map, and thus method 3 can be applied here. We therefore compared with two realizations of method 3, namely the holding endpoint method and the dumbing path method. Let's first look at the throughput. So the dumbing path method has a higher throughput than the holding endpoint method, but our method RHCR has a higher throughput than both of them. And the throughput improvement is by up to 7%. However, when we look at the runtime, both holding endpoints and dumbing path methods runs faster than our method. And this is because at every time step, the method 3 only needs to plan passes for a few agents. So the MapPath solver runs faster than the MapPath solver in RHCR. Therefore, if we want to improve the throughput and we have enough runtime, then our method is a better choice. But if we have very limited runtime and we don't care about the throughput too much, then method 3 is a better choice. The second experiment is conducted in a simulated sorting center. Here, the map is not a well-formed map, and thus method 3 cannot be applied here. Note that for method 2, where we plan paths for all agents at every time step, it is very similar to our method with w equal to infinity. And here we run RHCR with different w. So let's first look at the throughput. When we increase the w from 5 to 10 and until to infinity, the throughput actually does not change a lot. So the throughput improved for a given number of agents. The throughput improved by at most 2%. This indicates that when we're using a small time window, actually the throughput will not be affected by a lot. But when we look at the runtime, the size of the time window affects the result a lot. So when we increase the time window, when we increase W from 5 to infinity, the runtime can increase by up to 5 times. And as a result, a small W results in a higher scalability. For example, here, when we use W equal to 5, we can solve up to 1,000 agents. While when we use W equal to infinity, we can solve only 700 agents. To summarize, in this talk, I first introduced left-long MapHef and introduced 3 existing methods. Then I introduced our algorithm, RHCL, which solves a windowed MapHef instance for all agents at every h-time steps. There are some benefits of our algorithms. It works for all kinds of maps. It does not have to replan paths at every time step. It could significantly reduce the runtime of solvers, and it could still produce high-quality solutions. And in experiments, we show that RHCL can scale up to 1,000 agents in a simulated sorting center. And this ends my talk. Thanks for listening.